Hello. Hello, am I audible? Okay. Okay, so good evening, everyone. My name is Ranjan Bora, and I am a PhD research scholar at IIT Delhi. I am one of the TA in this course, Biomechanics of Joints and Orthopedic Implants. This course is instructed by Professor Sanjay Gupta from IIT Kharagpur, and already I have taken three tutorials in the previous 3 weeks, and today is the fourth week of tutorial. So in today's tutorial, first we will solve the assignment of week 3 from the previous week. Then after that, I will explain the concepts of kinematics and kinetics of biomechanics, and then musculoskeletal modeling. And after that, I will solve some numerical problems related to the musculoskeletal modeling. So first, I will solve the week 3 assignment. I think all of you have submitted the assignment, so I will go through the questions. First question was the lateral distance between the lines of the 2 feet is called as. I think all of you, do you know the answer? Anyone? Yeah, it is working base. Like from this figure, we can see the lateral distance means it is talking about this distance. uh, Means this is 1 feet and this is another feet, so distance between these 2 feet is working base. The second question is the distance between successive instants of heel contact of the same foot. It is talking about the same foot, so yeah, this length, stride length, because we can see this green colored foot is the same foot, and the red color one the opposite foot. Now, swing phase constitute percentage of gauge cycle. How much percentage? Yes, like this is a gauge cycle, and this is the starting point. Means the right initial contact when the heel of the right foot contact with the ground. That is the starting point, and that is at 0%. And first there is the stance phase. Right stance phase means the right foot remains contact with ground, and at 60% the right foot right foot gets off from the ground, and after that it remains in the air. Means it it does the swinging movement. So this percentage is 40%. Answer B. What happens to the time duration of swing phase when the walking speed increases? Yes, means when the walking speed increases, for most of the time our feet remains in the air. Means our feet for most of the time of the gauge cycle, our feet does that swinging phase. So, and there are very less time for stance phase. So more time for swing phase and less time for stance phase when we increase our walking speed. The energy consumption in gauge cycle is dash when the center of gravity of the body follows a straight line. What will happen, like during the gate, if we follow a straight line, the energy consumption is, yeah, because means if we follow a straight line path, then this what is the center of gravity? Our whole weight, like how what is our body weight, that gets concentrated at this point at the center of gravity. So if we take a zigzag path like this, if we take a zigzag path, then we need to travel more distance. That means we need to do more work to carry our body weight. So if we follow a straight line, that means the distance is minimum, and in that case we need to do the less work means the energy consumption is minimum. The human gait has dash determinants to minimize energy expenditure. How many determinants? Yeah, so these are the determinants: compass gait, pelvic rotation, pelvic tilt, lateral displacement, stance knee flexion, dorsiflexion, and plantar flexion. All these determinants are explained in the lectures. So answer is 6. Now the ratio of the time frame of stance phase to swing phase reverses during running. Is it true or false? Mm. Yeah, yes, you are correct. So during walking, we take the more percentage of stance. Like previously, we have seen during the walking, we have 60 percentage of stance phase and 40 percentage of swing phase. But during running, it gets reversed. Means the stance phase get reduced and swing phase get increased. So, uh, so it is a true statement. The gait abnormality where the stance phase is abnormally shortened in comparison to the swing phase is, yeah, yes. These are also other kinds of gait abnormalities like Trendelenburg gait and foot slap gait. Now, when the ground reaction force of gait disorder patients passes outside the body, the momentum around the joints, what happens to the momentum? Yes, like from this figure we can see this is the ground reaction force of a normal person, and it passes through the body. But if the patient has some disorder, gait disorder, then the ground reaction force passes outside the body and it increases the moment arm. Means if we consider from this joint, the hip joint, the momentum gets increased by this amount, so it is increases. For gait analysis, the usage of these sensors is restricted to the gait laboratory premises. Yeah, non-wearable. Now, clinical gait analysis involves dash measurements. Yes, yes, both objective and subjective. Uh, Technique is used for recording the electrical activity produced by skeletal muscles. Yeah. So in electromyography, what we do, we place a EMG sensor on the surface of our skin, and what it measures the electrical signals. Those are signals. Those are transmitted by our muscles. So it records the electrical activity. So option B is correct. Electromyography. Which of the following is a non-wearable sensor type? Hmm. Like we can see, these are the force plates. The other sensor type which are given, like goniometer, wireless EMG, accelerometers, all can be weighed, or all can be weighed by the patient. But force plates, we lie the force plates on the surface, on the ground, and the patient walk over the force plates. So it is a non-wearable type. Which is a major limitations of markerless system for optical motion tracking. Yeah, yeah. Like for the markerless system, we use these cameras, and these cameras have some limitations, like they are short range and they cannot operate without the sunlight. Means they require the bright sunlight. So option A is correct here. The DAS motion capture system works by identifying marker features which are used to track the motion of the body segments. Yeah, A is correct. Marker based. So in a marker based system, we place the means markers on the surface of the body of the patient, and using using the cameras we track. These are the cameras, you can see these are two cameras which are placed, and using those cameras we track the coordinates of these markers. The HIP 98 is a database of hip contact forces and gait data during various daily activities. Is it true or false? Yeah, it is true. How many independent markers are required per body segment to construct the marker axis system? Yes. So this is a marker axis system, and these are the markers. This is one marker, two, three. So we have three. single support phase constitute approximately percentage of the gauge cycle. How much percentage?
Sir, there are two single support bays, so I think this must be 80%. It's not be 80.
No, no. See, see, this is the gauge cycle. Like here, it is 0%. At 0%, it is starting, and at 100%, it is getting completed. So means you are talking about two gauge cycle, but those two are for different leg. But like if we consider our right foot, then this upper bar is the gauge cycle for right foot, and the lower bar is gauge cycle for left foot. See, for left foot, it is starting at this point, 0%. So means it is talking about only for one foot. Like see, for right foot, it has this right stance phase here and right swing phase here. And for this foot, there is only one right single support. Right single support, and remaining is right swing phase. Is it clear?
Okay. So I for double support, what will be the answer? Someone asked for double support. Let me see.
Yeah, double support, it will have 20, yes, because it has two.
Okay.
Mm-mm. So option B is correct. While running, this phase exists. Which phase exists?
So double support.
Yes. While running, there is no double support phase. Only the double swing phase exists. Yeah, Orindam B is correct. By reducing working base, the lateral displacement of center of gravity is, yeah, it is reduced. Like if we reduce this working base, then means if we reduce the distance between these two feet, then the lateral displacement means this displacement. The means the displacement of center of gravity in the lateral direction, it also gets reduced. So option A is correct. Okay, there was a one doubt from week 2 to assignment. I think you were asking about means there are two options. You can see like clavicle, scapula, and thorax, and another one is thorax, clavicle, and scapula. So for this case, what was the right answer?
Ready?
Yeah. See, why is it D here? Because this was the definition for closed chain mechanism, like the kinematic chain with every link connected through joints to two adjacent links. This is true. This is true for both the cases, means for C and D. But you can see here the terminal link meets enough resistance to restrain its free motion. Here it is talking about the terminal link. In C, the terminal link is thorax. So this is the thorax part, means, and we don't know about the mobility, about the means the degrees of freedom of thorax, how it can move. But in option D, we have scapula as our terminal link. But we already know this scapula is constrained from means it cannot move and it cannot rotate. It is written in our slides. So by looking at the terminal link here, option D is correct. Both chain represents the same chain only, this clavicle, scapula and thorax, but in option D the terminal link given as a scapula. That's why here D is correct.
Sure, but the scapula can glide over the thorax.
No, it is constrained. It cannot glide. Yeah, scapula cannot glide. These joints means only humerus can glide over this joint.
Okay. Okay. So that's why we used to reduce 1 degree of freedom when we deal with the scapula and thorax.
Yeah,
Right?
yes.
Because in the slide that has given 17 degrees of freedom for this system. In that we have reduced we have done -4 for this case.
Okay, means minus, it is degrees of freedom is minus.
Yeah, -2.
Yeah, minus mean it is fully constrained. Like it cannot move at all. Okay, now I will start the week 4 contents. First I will explain the kinetics of biomechanics, and related to kinetics, first we need to go through the equations of motion. So in kinetics, we'll use these equations of motion. These equations comes from the Newton's second law. These three equations, like summation fx equal to ma in x direction, summation fy, ma, a is the acceleration and m is the mass, uh, ma in y direction, and summation m equal to I alpha. Here alpha is angular acceleration and I is moment of inertia. So we'll use these equations to solve the problems related to kinetics. Now we'll study the what is a mass moment of inertia. Like in this figure you can see there is a body segment, and we are dividing the body segment into n parts, means dividing the body segment into n parts, and each part has its own mass. Like part 1 has mass m1 and it is at a distance of x1 from this left end. We are taking the left end as our origin O. So from O, the first part has mass m1 and the center of gravity of m1 is at a distance of x1. Like that, the center of this, like the distance of center of gravity of mass m2 lies at a distance of x2 from O, and so on. The distance from the origin to the center of gravity of mass mn is xn, and the whole total mass is capital M. So how, according to the definition of mass moment of inertia, the mass moment of inertia is given as it is a summation of moment of inertia of each mass. Like for the first mass, the moment of inertia is m1 x1 square plus m2 x2 square uh, plus mn xn square, and this I is about this point O, means about the axis passing through O. So this I is this expression summation I equal to 1 to n mi xi square. Now there is one theorem which we need to use to solve the problems, that is parallel axis theorem. What is a parallel axis theorem? It is given as I naught plus mx square. That means if we want to find out the moment of inertia about this point, about the point here m, capital M, then first we need to know the what is moment of inertia about I naught. Here I naught is the moment of inertia about the center of gravity. So I will take another example. Like this is a body link and this is I. Sorry, this is the center of gravity of this link, and we want to find out the moment of inertia about this point. So, and this distance is x. This has a mass m. So I is given as I naught plus mx square. I naught is the moment of inertia about center of mass. X is the distance between center of mass and center of rotation, and m is the mass of segment. So is it clear? Anyone has any doubt? Okay. Now we'll solve this problem. Please read the problem. In this problem, it is asking the magnitude and direction of moment m naught that must be generated by the knee muscles to produce a tangential acceleration of 20 meter per second square at the ankle in the figure shown. Now the moment of inertia of the lower leg and foot about the center of gravity is, this is the lower leg, this is lower leg, and this is foot. Moment of inertias are given. Now the center of gravity of lower leg and foot are located at 20 centimeter and 50 centimeter along x-axis. That means this is 20 and this is 50, and along y-axis means this distance. This distance is 2 and this distance is 5. So how we will solve this problem?
will sum over the moments about the knee of this arm.
Yeah, means here the moment of inertia is given about their center of gravity, means about this point and this point. But we need to find out the moment of inertia about the knee joint, about this point, about point O. So we need to use the first we need to use the parallel axis theorem to find out the moment of inertia about point O. And again, means this is point O, and this is the center of gravity of lower leg, CG of leg. And what is this distance? This is 20 and this is 2. So we know the we know center of we know the moment of inertia about this point, CG, about the center of gravity of leg, lower leg. So now we need to find out the moment of inertia about point O. So for that, what we need? We need this distance, the perpendicular distance between point O and the center of gravity of leg. So what is this distance? Let us take this is as d1. So we have d1 equal to plus 2 square equal to, it is almost 20, it is coming as 20.1. So d1 is 20.1. So what will be moment of inertia about point O for leg? It will be ICG leg plus mass of leg dot d1 square. So it will be moment of inertia about CG is given 0.06 plus mass is given 3.537. d1 is 20.1 centimeter, 0.2 in meter square. It will be 0.2 kg meter square. So is it clear? Anyone has any doubt?
It's clear.
Okay. And similarly, we need to find out the moment of inertia about point O for foot. Foot is located at a distance of 50 and this was, I think, this was 5. So this is ICG of foot, and this is point 0, and this is D2. D2 is 50.25 centimeter. So moment of inertia about point 0 for foot will be foot plus mass of foot dot, it is 0.02, mass of foot 1.11, d2
So what is the mass of food? Is it given?
yeah, it is given. See this one.
1.1.
Yeah, yeah.
Okay.
Hmm. So it is coming 0.3 kg meter square. So what will be the combined moment of inertia for both foot and leg?
So we will add these two simply.
Yeah, yeah.
0.3 and 0.2.
Leg plus foot. 0.2 plus 0.3, it will be 0.5. So now we have found the moment of inertia about point 0, but in the question it is given the tangential acceleration. It is given a linear acceleration, but we need to find out the uh, angular acceleration, angular tangential acceleration. So what is the formula for that? We have one formula, 80 divided by r is the radius. So it is given 20 and it is 50 centimeter. This radius will be this much, 50 centimeter, because about this point, this ankle joint, it is situated at a distance 50, and if we want to take the perpendicular distance, that also we can, but we need to take this 50 as our distance, because we are considering the direction of this tangential acceleration, means perpendicular to this radius. It will be perpendicular to the radius, that's why we need to consider this distance 50. 20 by 0.5, it will be 40. Its unit is radian per second square. So now we'll use the equations of motion which we have discussed earlier. What was the equations of motion? We have summation of moments equal to I alpha. So moment about point O, I about point O. What will be the summation of moment about point O?
So it will include the movement by the weight of the limb.
Yeah, we need to consider those also. This moment due to W1 and W2.
Yes.
So this direction M0, direction of M0 is here is given, it is anti-clockwise. So we will take that direction as positive, means anti-clockwise direction as positive and clockwise direction as negative. So it will be M0 plus, sorry, it is positive, and uh, moment due to this weight W1, it will be negative because it is in clockwise direction from with respect to point O, and it will be W1 multiplied by Z. W1 is, sorry, it will be M1 multiplied by Z. M1 is the mass of this leg, which is given as 3.537 kg, and G is the acceleration due to gravity, and this distance is 20 into 0.2 minus M2Z into 0.5. I notice 0.5 m alpha. See, with respect to point O, this tangential acceleration, it is in anti-clockwise direction, right? With respect to point O. So we will take it as positive because we are considering this anti-clockwise direction as positive. So means we need to consider the sign conventions for alpha also for tangential acceleration. So alpha is 40. Now from this equation we can find this value of m0. It will be 3.537 to 9.8. 0.5 plus 0.540. It will come as 32.37 Newton meter. So is it clear?
Yes, sir.
So the value of m0 is coming as positive. That means whatever the sign convention, whatever the direction shown in here, the anti-clockwise, the m0 will come in that direction only. Means knee muscles should produce a moment in the anti-clockwise direction if the foot is raising, if someone raises his foot in the upward direction. Next we will see joint kinematics. So in joint kinematics, like in the week 3 lectures, sir has explained like how we can measure the joint kinematics. Joint kinematics means the velocity, then velocity and accelerations of the joints, and some angular data like the angle, like during the movement of a person, how much the hip angle varies with respect to the gait cycle. Those data comes under the joint kinematics, and we measure those data in the gait laboratory. Like in the week 3 contents, it is already there different techniques for measuring the joint kinematics. So in the gait laboratory, we measure the coordinate data of the markers. Like we place various markers around the body of the subject, and when the subject walks over the force plate, using the different cameras which is installed in gate laboratory, we can measure the coordinates, and using those coordinates we can measure like velocity, acceleration, all those data, and those data can be used later to find out the joint reaction force which get produced during the movement of the human body. So first step is to measure the data in gate laboratory, and using those data we find out the velocity, acceleration, and that is the joint kinematics. So there are various methods using which someone can calculate the different parameters. Like there is one forward difference and one is central difference. Here it is, I am showing the central difference approximation, and using this approximation, like if we know the coordinate data at a time instant of I plus 1 and I minus 1, then we can find out the velocity at the time instant of xi. And if we know the time variation, so using this equation we can find the linear velocity along the x direction, and this approximation is known as the central difference approximation. Similarly, we can find out the angular velocity. What will be the angular velocity? Angular velocity will be omega theta I plus 1 minus theta I minus 1 to delta t. Its unit will be radian per second. Here thetas are angles of the joints. Similarly, the linear acceleration in x direction at the ith time instance can be given by this Vx I plus 1 minus Vx I minus 1 divided by twice delta t. And in the angular coordinates, we can find out the angular acceleration. Angular acceleration alpha will be omega theta I plus 1 minus radian per second square. It is at the time instant of theta I. Now, using those equations, we'll solve one problem. See, in the gate laboratory, we place different markers. You can see these are the markers. Base rib cage, we place one marker here. Then we place one marker at greater trochanter hip. Then we place marker at the knee and lateral epicondyle of thigh. Then we place a marker at head of fibula. Then on the foot, we place marker at ankle, then heel, then at the toe. So using the coordinates data of different markers, we find out those velocities, accelerations, all those data. Here it is asking from the coordinate data, calculate the acceleration of the knee in the x direction for frame 3. So these are different frames recorded in a gate analysis, in a gate laboratory. So it is asking for this frame, for third frame. So, and these are the coordinates data of this marker, which is placed at knee. So how we will solve?
Since we have to calculate for the front three, so we will use the data of 2 and 4
Yeah,
for calculating velocity initially, and after that we will calculate.
yeah. First, we need to calculate the velocities. Right? For frame 3, like acceleration for frame 3 will be velocity for frame 4 minus velocity for frame 2 divided by 2 delta t. Here you can see the delta t is not same, like this delta t and this delta t. So it will be delta t1 plus delta t2 because both the delta t are different. Again, how we will calculate the v4? V4 will be x5 minus x3, x5 minus x3 divided by delta t1 plus delta t2. What is x5 here? X5 means the fifth frame, which is 0.5613 minus x3 is 0.485. Delta t1 means 0.57 minus 43, and what is delta t2? T2 is 0.043 minus 29. So from this expression you will find out the velocity at fourth frame. It is coming as 2.725 meter per second. See, these times already gets cancelled. 0.4, 0.40 and 0. Minus 0.0. So we can write as means we can also write it as T5 minus T3. Now V2 will be x3 minus x1 x3 485 T3 0.029 T1 is 0, so it will be 2.67. So we have found V4 and V2. Now we can find out A3. 3 will be 4 minus V2. We can also write as T4 minus 2.725 T4.043. It is 1.81 meter per second square. So is it clear?
Yes, sir. It's clear.
Okay. So this is a problem involving the linear coordinates. So there can be problem on angular coordinates also. Like here, the coordinates will be given in angular coordinate system, theta 1 and theta 2, and using those data, we need to find out the angular velocity and angular acceleration. The procedure, yeah,
Sorry, sir. If we are used to find the acceleration in y direction, then
mm.
we will use the coordinates of y.
Yeah, coordinates of y, yes.
Okay. This means that they are independently formed.
Yes. Okay, so next is musculoskeletal model. What is a musculoskeletal model? In musculoskeletal model means there are different softwares to develop this musculoskeletal model. This is a model from OpenSim software, and that software is mainly used for the research purpose involving different biomechanics. Like using that software, we can find out the joint reaction force, then muscle forces produced for different time instance of our gait cycle. So And first we need to develop this musculoskeletal model, and the musculoskeletal model consists of the rigid bodies. Rigid bodies are the bones, means these bones we model as rigid body in the musculoskeletal model, and these bones are connected by ideal joints. Like this is the knee joint, and here beneath the muscles there is hip joint. So we connect the bones with the help of these ideal joints, and actuators are these muscles, these red colored ones. These are the actuators muscles. Now there are different algorithm to solve the problems related to musculoskeletal model. There is one algorithm which is known as inverse dynamics. Like in the inverse dynamics, we uh, we calculate the joint force and moments, and the input parameters are these ones. Like from the anthropometric data, we get the segment masses, lengths, and moments of inertia, and from the marker position data or from the gate analysis, we find out the segment displacements, and using the force platform, means using the force plates, we get the ground joint reaction forces, ground reaction forces. And using this input data, first I have already shown, like using the marker position data first to evaluate these velocities and accelerations, segmental velocities and accelerations. And using the anthropometric data and force data, we develop the equations of motion, and using those equations of motion, we get the joint force and moments. And means in the inverse dynamics model, we model as anatomical model as a link segment model. Means we model different parts of our body as a link. Here you can see for our leg, the leg can be modeled as a three link member. Like this is for this upper part of the leg, this member is for lower part of the leg, and this is for foot. Now we can segment out each part. Like you can see from free body diagram, we can represent this foot as a one member. Then we can represent this lower leg as another member, and upper leg as uh, another member. So like this right hand side, if we assemble these members of the right hand side, we get we get the we get our leg, which is represented in the left hand side. Like you can see, this is the ankle joint. In the ankle joint, these are the reaction forces at the ankle joint, rx3 and ray3. And in the ankle joint, in the member 2, you can see the directions are opposite. Means this rx3 direction is opposite to the direction of rxt, which is in member 3. So if we assemble this member 2 and 3, these forces gets cancelled out, and this moment also get cancelled out, and we will get this point 3. This member 2 is shown here. So we use these concepts to solve different problems. Like first first what are the data we can measure? We can measure the ground reaction force. And where does the ground reaction force act? Ground reaction force act at here, means at this point, means on the foot, or on the foot with respect to the position of the foot. So here the ground reaction force X, and we know the ground reaction force data. And using the ground reaction force data and the anthropometric data for the foot, we can find out this Rx3 and Ry3 and this moment which is getting produced at the ankle joint. So using those data, uh, we can find out the joint reaction forces at the knee, at our knee, this Rx2 and Ry2, and the moment which is produced at knee joint, which is M2. And similarly, using those knee joint data, we can find out the joint reaction forces at the hip joint, this Rx1, Ry1, and moment M1. So using the inverse dynamics approach, we can find out the joint reaction forces at any joint in our body if we know the input parameters, which are the ground reaction forces and some anthropometric data of the body.
So
Now,
why it is called an inverse dynamics approach, inverse dynamics method? Why it is called?
yeah, means there is another approach which is known as forward dynamics. And in forward dynamics approach, I think we already know this uh, forward dynamics approach. We already know the force parameters, means force values, or I will explain in the next class. Is it okay?
Yes.
Okay. Okay, so we'll solve one problem. During the toe phase of the gait cycle, the ground reaction forces Rx and Ry acting on the foot are found to be 90.8 and 612.1 Newton. Calculate the joint reaction forces and net muscle moment at the ankle. The subject's mass is given 65 kg and the mass of the foot is 0.9 kg. So this is the ankle joint, point O, and here it is asking the joint reaction forces and net muscle moment at the ankle. So what is the first step? We will assume one reaction force in this direction, Rx1, Ry1, and we will assume one moment as M. And weight of the foot is given as 0.9 kg. It is acting through this point, this W. W is 0.9. It will be 0.9 into Z, which will be 9.8. So how we will solve? We will use the equations of motion, which we have studied earlier. What is the equations of motion say? Summation fx Here we are not given any acceleration parameters, so we will consider it is a static problem. Means if the acceleration parameters are given, then we need to solve using the dynamic equations. So there is no acceleration, so summation of forces must be 0. Means this position of the foot is in static condition.
So, can you please at least say the things that you have said in the last 10 seconds? I
Sorry.
was so please repeat what you have said about the static analysis.
Yeah, means we are not given any acceleration values, right? The linear acceleration and angular acceleration. If in the question any acceleration values are given, then we will solve the problem using the dynamic equation, which is the dynamic equation summation f equal to ma. This
Okay,
equation, since here acceleration is 0, so summation f equal to 0.
okay, okay.
Okay,
Got it.
so summation fx, if we do that, rx1 plus rx equal to 0. From here rx1 will be minus rx, which will be minus 90.8. And similarly summation fy equal to 0, that will be ry1 plus ry minus w. So ry1 will be w minus ry. This will be minus 603.2.
Sir,
Yeah,
sir, why you have taken W as point 0.9? I think it must be the subject mass.
no, no, excuse me. For means for this problem, we are taking this as our system, the foot, and here it is, the point here it is shown is the center of gravity of foot. So why the subject mass is not considered here? Because we are already considering this ground reaction force, and this
Okay, okay.
and this vertical component of reaction force is coming due to the mass of the subject. That's why we are not considering that subject mass here. Is it clear?
Yes, sir, it's clear.
Okay. Now we need to find out the moment. Moment about point O is 0, and that will be m is in the anticlockwise direction. We will take anticlockwise as positive, and m minus w. Because of ry, ry will also produce the anticlockwise moment. ry into 9. So n will be minus here 3 I have taken in centimeter, so to convert it to meter I need to means these data are given in centimeter. Means ry is 612.1. So it will be minus 54.82 meter.
Sir, RX will not produce any moment.
Okay, sorry, yeah, rx will also produce one moment. Okay, this distance is not given, so I will take it as 15 15 centimeter. So Rx will produce a anti-clockwise moment. Anti-clockwise. One second. Rx plus X to minus. It is coming minus 68.44. So we are getting as a minus means whatever the direction we assumed in our case, it will be in the opposite direction. For all the reaction forces Rx1 Ry1, we are getting minus, so Rx1 will act in the opposite direction, and Ry will act in the downward direction, and moment M will be in the clockwise direction. Okay, so it is
Sir,
clear. Yeah.
in the examination, this type of data are given, or
Yeah.
we have to assume sometimes.
No, it will be given.
Okay, sir.
Mm-mm. Okay, there is one more problem. So in this problem, you can see, first you read the problem. It is given the accelerations. So in this problem, the accelerations data are given. So it is not a static problem. Means we cannot use the static equations. We need to use the dynamic equations. And the mass is given as 1.12 kg, and moment of inertia is 0.01. We need to find out the muscle moments and reaction forces at the ankle joint. These Fx and Fy, you can see Fx and Fy, these are the ground reaction force. And these data are coordinates, means coordinates of the markers. One marker is placed at this toe, then one marker placed at the center of the foot, and one marker is the ankle joint. So these are the coordinates given. Now we have those equations, summation fx equal to max. So what are the forces acting in the x direction? We have Fx, which is ground reaction force, plus Fax. Fax is the joint reaction force at ankle. Here A is the ankle joint. We have only these two forces equal to mass. Mass of the foot is 1.12 into acceleration along the x direction is 3.25. So using this, we can find out Fax minus 160.25 will be minus 156.61 Newton. Means the direction of Fx will be opposite to what we have assumed here. And similarly, we can use summation Fy MMI. Forces in y direction are Fy Fay minus 1.12 into 9.8 equal to mass is 1.12, acceleration in y direction 1.78. So using this we can find out Fy. It will be minus 752.9 Newton. Now to find out the muscle moments, that means it is asking the moment ma. To calculate the moment ma, we will do the moment equilibrium about the center of gravity of foot, because yeah, see, in the question it is given the moment of inertia of the foot is 0.01 kg. This moment of inertia about this point, about the cg, means cg of the foot is here. So we will do the moment equilibrium about point cg equal to I alpha. Because this I is already given in question and alpha is also given in the question, and these two values are with respect to cg, with respect to point cg. Is it clear?
Sir, in the equilibrium equation of in the y direction,
Hmm.
sir, Fy plus Fay.
Hmm.
What is this 1.12 to 9.2? Okay, okay.
This
Mass
is,
of,
yeah, because of the weight of the foot.
okay.
So if we do the moment equilibrium about point cg, we need to find out these distances. Because with respect to point cg, these forces will generate moments, this Fx, Fay, Fx and Fy. So we need to find out the moment terms. This distance will be, I think this distance will be 7.6, and this distance will be 5.6, and this distance 4.6. Seven point So if we do, yeah,
Sir, can you please tell the coordinate because it's not visible clearly, sir. The coordinate of A,
it is
let's say,
89.7,
okay, okay, sir.
89.7 comma 16.
Okay, okay. CG,
CG is 95.3
okay, sir.
comma 8.4,
Okay,
and point M is 100.9
100.9.
comma 0.9. Okay, so with respect to point CG, see here one moment MA, and that moment is acting in anti-clockwise direction with respect to point CG. So we'll take as anti-clockwise as positive. We'll follow this sign convention, this anti-clockwise as positive. So MA and FAX and FAY will produce clockwise moments. That will be negative, minus FAX into 7.6 minus FAY into 5.6, and this Fx and Fy will produce anti-clockwise moments. This will be positive, Fx into 7.5 plus Fy into 5.6, and this weight of the foot will not produce any moment because it is passing through that point. So we will not consider that force equal to I alpha. I is given 0.01 and alpha is minus 45.35, and minus Fx value, we have calculated Fx is minus 156.61. Fay minus 752.9 plus 160.25 765.96 equal to minus. So using this equation, we will get the value of MA. Oh, one thing I forgot to mention. These coordinates are given in centimeter. So these distance data are in centimeter. So we need to divide by 100. So if we do that, we will get minus 109.4 Newton meter. That means this anti-clockwise direction is showing this will be not the direction. The actual direction will be in the clockwise direction of moments. And also for fx will be in this direction and fy will be in the downward direction. So is it clear?
Yes, sir.
Okay. Okay, if you have any doubt, then you can ask. I think that was for today.
So I think I'm clear, sir. There
Mm-hmm.
is no doubt. I think it's clear what
Okay,
you
okay.
have told
Okay,
me.
yeah.
It's clear.
Okay, then we can close if we don't have any doubt.
Sir, sir, one thing.
Yeah.
We have done the summation of movements about the center of gravity, CG.
Mm.
The next line
Mm.
we have written on the right hand side is 0.01 into this minus 45.35.
Yeah.
Okay. So I was given 0.01.
Mm.
Okay. Sir, okay, sir. One thing more. So please review the part of the slide where you have given the questions. That is problem number 1, 2, 3, 4. The slide of the questions so that I can have a screenshot of that from
Okay.
my.
Okay. Yeah, this question you can take. Uh, you want to take the screenshot now? Yeah, Mohammed.
Yes, sir.
You want to
I have
take the
taken it.
screenshot?
Yes, sir. Yes.
Okay. So next this one.
Sir, one. Sir. Okay.
Then, anyways, I will upload these slides.
Okay, sir. Okay.
This one you can take.
Sir, I have taken.
Mm. Next this one.
Sir, taken.
Okay.
Thank you.
Okay, then we can close if you don't have any doubt. We'll again meet next week on the same time, Saturday.
Okay, sir.
Okay. Thank you
Thank
for
you, sir.
joining. Yeah.